All right, welcome to this explainer. Look, if you're tuning into this, you already know that AI is the defining technology of our era. You see it embedded in your dev tools, your algorithmic feeds, and pretty much all of your enterprise software. But today we're going to move way past the buzzwords and the hype cycles. We're actually going to crack open the hood and examine the real architectural mechanics of how these models function. Okay, let's dive right in. So here is our roadmap for today. We're going to start with a quick refresher on demystifying artificial intelligence, then look at how AI actually works, classifying AI systems, how AI models learn, the real-world impact, and finally, the challenges ahead. Okay, kicking things off with Section 1, Demystifying Artificial Intelligence.
So just to set a really quick baseline here, we all know AI isn't magic, right? It's basically just a simulation of human reasoning. And it manages to do this by ingesting massive amounts of data, spotting these deeply hidden patterns that would literally take humans lifetimes to find, and then continuously refining its own algorithms through iterative feedback.
Now, right underneath that broad AI umbrella, we've got machine learning. Think about traditional software for a second. You have to write explicit, rigid if-then rules. But for complex tasks, the number of rules becomes computationally impossible. Imagine trying to write an explicit rule for every single possible way a human hand could write the letter A. You'd be coding forever. Machine learning bypasses that entirely. It just finds the statistical relationships in the data completely on its own.
And then, of course, there's generative AI. This one is absolutely everywhere right now, and it's fascinating because this isn't just about mimicking or categorizing existing data. It's actually synthesizing vast latent spaces into net new outputs. Whether it's compiling functional code, generating hyper-realistic art, or drafting complex legal text, these models are predicting the next logical sequence to create something that literally did not exist a second ago.
To kind of round out these core concepts, let's contrast two really powerful branches. On one hand, you have natural language processing, or NLP. Think of NLP as the flexible communicator. It powers the dynamic voice assistants and semantic search engines we use every single day, seamlessly handling the messy, highly unstructured nature of human language. On the other hand, we have expert systems. These are like rigid, hyper-specialized doctors. They don't chat with you. They rely on incredibly deep, domain-specific rule bases to do things like diagnose rare diseases or calculate risk in high-frequency trading.
Moving right along to Section 2, How AI Actually Works.
Let's walk through the actual internal mechanics here. And instead of using that classic, somewhat basic, is this a picture of a cat problem, let's look at detecting a fraudulent financial transaction. Step 1 is data collection, ingesting millions and millions of historical credit card swipes. Step 2 is processing and learning. This is where algorithms identify really subtle behavioral features, like maybe a sudden geographical jump in small purchases. Step 3 is model training, which means adjusting internal mathematical weights to accurately flag anomalies. Step 4 is decision-making. Boom, a brand new swipe happens, and the system decides in milliseconds if it's fraud. And finally, Step 5 is feedback and improvement. If a human overrides a blocked card, the system learns from that mistake and refines its threshold for the very next time.
All right, Section 3, Classifying AI Systems.
When we categorize all these different AI systems, we typically look at them through one of two lenses: capabilities or functionalities. On the capabilities side, everything you and I interact with today is narrow AI, meaning it's highly optimized for very specific tasks. Things like general AI, which is human-level intellect across multiple totally unrelated domains, and superintelligent AI, well, those remain completely theoretical right now. Now, looking at functionalities, we have reactive machines that only respond to current inputs without any context, and then we have limited memory systems. A great example of that would be modern self-driving cars, which leverage a constant buffer of recent past data to improve their immediate dynamic decisions on the road.
Which brings us to Section 4, How AI Models Learn. This is super important because the type of data we feed a system dictates its entire learning paradigm. First up, supervised learning. This is essentially the teacher-student model. You feed it clearly labeled data with known outcomes, which is absolutely perfect for building something like a highly accurate spam filter. Unsupervised learning, though, acts way more like a lone explorer. You give it massive amounts of unstructured, unlabeled data, and it goes out and discovers hidden mathematical clusters on its own, making it an absolute powerhouse for things like customer segmentation. Finally, there's reinforcement learning. This is the trial and error approach. It operates in an environment driven strictly by programmed rewards and penalties. And actually, that's exactly how we train autonomous drones to navigate complex physical spaces.
Let's pivot slightly for Section 5, Real-World Impact.
When you step back and look at the sheer scale of this technology today, it's basically acting as a tireless, 24/7 co-pilot across every major sector. And it doesn't just automate repetitive workflows, it actually anticipates needs. In heavy industry, for example, AI is analyzing microscopic acoustic vibrations to predict a machine failure weeks before a multi-million-dollar breakdown ever occurs. In global finance, it's catching synthetic identity fraud in milliseconds. And over in healthcare, we are seeing models detect anomalous cellular growth on patient scans with a level of precision that deeply enhances an expert physician's diagnostic toolkit. It's a total game changer.
But of course, Section 6, the challenge is ahead.
Because, look, this massive level of scale, it is absolutely a two-sided coin, and we are tracking some really significant friction and risks. The sheer volume of data required immediately triggers incredibly complex security and privacy vulnerabilities. There is also the persistent black box problem. This is a severe lack of transparency, where it is often mathematically impossible to explain exactly how a deep learning model arrived at its final output. Plus, if the initial training sets contain statistical skews, those biases just amplify at scale, leading to genuinely unfair real-world outcomes. And we can't ignore that the huge efficiency gains we just talked about are driving a major macroeconomic shift, which is necessitating unprecedented workforce reskilling as legacy roles get entirely automated.
Which really just leaves us with this one massive question to chew on. As artificial intelligence achieves this unprecedented efficiency and fundamentally transforms major global industries, how do we actually strike that perfect balance? How do we harness its immense computational power while effectively managing data privacy, mitigating those systemic biases, and supporting the millions of human workers who are currently navigating this massive automation wave? It is a complex puzzle for sure. But understanding the core mechanics of how AI actually works, just like we've explored today, well, that is the absolutely crucial first step towards solving it. Thank you so much for joining me on this explainer, and keep learning.